First, let's work out the question for attendance, and then we'll talk about the question from last week. Conditional probability, maybe we should leave that after we talk about conditional probability. Realize I may have not ordered these questions. Better order. Let's try this one. Let me try to explain it with a Venn diagram. I feel like we should talk about the multiplication rule before a lot of other questions, but this one I think we can try to visualize it with a Venn diagram. The probability that a visit to a primary care physician, in short, it abbreviated as PCP, results in neither lab work nor referral to a specialist is 35%. So if we call the lab work as event L, so if we use L as event needing lab work, if we call needing a specialist as event S, as in specialist. Okay, and then the first sentence can be made a little bit shorter, and that is probability of not a lab work and not a specialist. So you might write not a lab work, so L prime, and not a specialist, so S prime, or you can write SC, but on the keyboard it's easier just to write prime for the complement thing. This has a probability of 0.35, 35%. So we try to shorten the explanation. Is it visible? Is it okay? So sometimes I feel like what I was writing on the board is not visible if you're sitting behind the classroom. So that's the first one. And of those coming to the PCP office, 30% are referred to a specialist and 40% require lab work. Okay, basically coming to PCP office in this question is as a whole. So the second sentence basically is saying P probability for specialists for S is 30%. Probability for lab work is 40%. So you can kind of shorten that as P of lab work. S specialist, P of S is 30%. And then lab work is 40%. So you can write P of L. So S and L are the two events we're talking about. So this is trying to kind of write out all the information in a slightly more concise way. And the final questions. Now, assuming that we have all the information that we need so far after reading the whole question, and then the last question is calculate the probability that a visit to PCPs always result in both lab work and referral. So pay attention to the word and. So this is a intersection. This is a joint event. We want to find probability L and S, lab work and specialist. So with that, the writing of the questions is we want to find P of S and L. So it's an and event, not an or event, and this is what we need to calculate. Okay. You can try to roughly estimate what's going on. You can graph a Venn diagram. There's only two things in here. One is needing a specialist. The other one is needing a, let's use a different color, needing a lab work. So this is letter L. This is letter S. It says the part that does not need any of those is 35%. So what's on the outside, you write 0.35. And that is indicating that the S or L, okay, from the first thing that you read, this one. So from this, you immediately can get the complement of that, which is S or L or S. So probability of L or S. Opposite of not L and not S. To see if you want to do a complement of that, because of the De Morgan law, it has to be L, opposite of L prime, not S. L would be L. Opposite of and would be or. So the logic opposite of S is S prime is opposite S. So kind of reverse the logic into finding complement. That will be the 0.65. So figure out logically how to convert one information to another one will be helpful. So this is 0.65, not 35. You do 1 minus 0.35 is 0.65. And having all these information ready, you kind of see that this portion is 0.65 because the outside is 0.65. But then this portion is 0.3, this portion is 0.4. If you add 0.3 and 0.4, it will be 0.7, but in fact it's 0.65. What happened to the other 0.05? Right, it will be both. So the answer to the question, all right, I hope I had explained it enough so it won't be difficult to find out. So I guess I'll kill this to app to get to the right app. Have your card ready, and let me make sure the orientation is at 90 degrees. Thank you.
Oh yeah, I will. It was the written orientation. Okay, so now
So your name is highlighted, your answer is recorded. The lower corner. Okay, the answer should be A, isn't it? Yeah. So because that would be the overlapping. Yours has a wrong one. Did we adjust the letter? It's A. Did we already?
Okay, yeah.
Right, so you're gonna have to switch it.
Okay.
The A would be the D.
Yeah.
Uh-huh.
A is the D.
Yeah.
Okay.
Because the orientation, I changed the orientation that causes the difference tonight. Was it A, then B, then, okay, so that's the rotation. Kind of like rotating the whole thing 90 degrees.
Okay.
So then A would be,
A is right here.
yeah, A should be on top. All right, thank you. That allows me to record the attendance questions. There are We have 8. Right now, let me see. Oh, he left. Okay. Do you have any questions for last week's assignment? The 1.1 and 1.2? Any questions?
I have a more question for 1.2 problem 9.
Okay. Your question is which one?
Problem 9, so basically, like, I was just struggling to, like, complete the book. Like, all words.
All right. In how many ways can 4 different novels, 3 mathematics book, and 1 biology book be arranged on bookshelf? If the book can be arranged in any order. The first question, if we don't care about the subject does not matter. All you care about, there are different books, so 3 different novels, 3 different math books, 1 biology book. So the math book, they're not the same book, and the novel are not the same novel. Therefore, there are actually 8 different books. Next question. So if you are just arranging 8 different books on the shelf, the order matters. So in this case, since the order matters, the number of arrangements, if you think of it, it's kind of like the first book, and then second book, and third book, and fourth, and fifth, and sixth, and seventh, and 8. So it's like having 8 spaces you have to fill out. When you try to decide what would the first book, you have 8 books to choose from. So the first step is to choose who's going to be the first book. And in that case, you have 8 number choices. For the second book, how many choices? 7, right? You already have a book at the first book. Once you already put a book there, you only have 7 books in order to decide who's the second book, right? So your number of choice reduce because once you figure out a choice there, you're laying things out, so there's no repetition. Therefore, the second book, you only have 7 books to choose from. Once you have the previous book decided in the same order, after that we have 6, and then 5, and then 4. These are multiplication relation because these are the steps. So every step cannot be skipped. If it's steps, then relation between them is multiplication. So we were supposed to multiply them all. Now, the calculation of multiplying an integer and then multiply the next integer below it and keep going until you reach number 1. This is the factorial. So answer to the first question, since we don't have any special requirement, there will be a factorial. All right, then we start having a requirement. B says, what if we want all the math books, which is true, right? When you try to arrange, my daughter last week came home and then she started like rearranging in our hallway, their books. They were really messy because of all the boys. And then my big girl, she's like, she can't handle the messiness, so she started organizing it. So in the spirit of trying to organize, we tend to try to figure out what are similar books. For example, you probably want to put all the math book together, all the science book together, all the novel together. That's mostly the way to think. There are also other people, though, they prefer having the book order in the like the letter. All the books start with A and then B and then C. There are different ways to arrange things so that it's easy for you to find it. If you go to the library, all the library books, the physical book, they're actually ordered in letter. And then I think different subjects have different letters. So the fundamental way that they organize book is based on subject first and then names. And that's how it is. So what are we that made it easier for us to find books? So anyway, if we put all the math book together, the novel all together, Since there's only one biology book, so it doesn't really matter. So in this case, if you have the math book all together, then you can think of having all the math book binded together. And you have math book, and then novel and biology. In that case, it's kind of like having three things to choose from. You have math, and then you have biology, and you have novel. So A and B and three of them. Now, you can have math and then biology and novel, or you can have math, novel, and biology, or you can have novel and math and biology. So this is kind of arrangement of three things. So you have three space to choose from. The number choice rearranging three things, there are 3 times 2 times 1. That's how many choices we have. But then you have 4 different novel, right? Those 4 different novel are all in one of the spots. And those 4 different novel can have different arrangement. They're all together, but you might have novel 1, novel 2, novel 3, novel 4. Or you may have novel 4, novel 1, novel 2. So these 4 books can be arranged. So how many arranged books, if you think about just the novel book in itself, assuming that you already determined this is all the novel, this is all the math, this is biology, but all the 4 novel, they can be rearranged, right? They can so in that order, 4 novel books, the number of possible arrangements for factorial. The reason for that is still 4, 3, 2, 1. That's how many choices we have for the 4 books, right? Same idea, the 3 different math books, how many ways to rearrange them? 3, 2, 1. So that's how you arrange 3 books. So that's 3 factorial. Basically, the calculation is 3 factorial times 4 factorial times 3 factorial. If you see the calculation, you might wonder why we're doing that. What was the purpose for each of the factorial? They actually do have different meaning in the calculation. So that should be how we answer the second question. You might have different number, but I think the logic is similar. Last one, if the math book must be together, but other books can be arranged in any order. In that case, the math book in itself, all the math books are together. So inside the math book, you still have the 4 factorial. 4 factorial, how many choice for there's 3 math book, right? 3 factorial. That's how you arrange the 3 math book. Now, once it's already arranged, you just bind it all together and then keep that order. And then you think of all the 3 math book as already together as a whole. And then the math book plus the other book. Math book is 3 book and the other book is 5, right? So it's 5 other book plus the math. 5 plus 1 is 6. Since we don't care their order, they can be in any order. So that will be 6 factorial. That is having the math book ordered in itself, and then just tie them together with rope, and then we start rearranging the other one. I hope that kind of makes sense.
I think so.
So it does take some thinking. It's like how many objects are we arranging? Sometimes it's 6, sometimes it's 3, and sometimes it's 4, depending on what you are arranging. The first one is rearranging, arranging 8 of them. This is all 3. So this is all 3. We have different number for your assigned question, but the reasoning are similar. The questions. You can write down your assignment and then we can compare. You might have different number. Do you have different number?
I do, but I'm working. I'm also double checking on mine as well. Make sure that
Any other questions? Right, so far we only talked about the additional, so I feel like maybe it's time to talk about multiplication rule, and that has some connection with conditional probability. So let's pull out the section 3. We can have a bigger variety of questions to talk about. All right, 1.3, we're going to talk about conditional probability. Conditional probability and the regular probability, what's the difference? The conditional probability is when you are thinking about if you have 2 different events, one of them happened first, and how does that affect the second event? All right, let's look at example, just try to use example, try to think about how it's relates. So for example, in this table, we have some, I think there are flowers. I assume there are flowers. So some flower blossom earlier and some late. And now we have red and yellow. So the total in each case, for the early, the total is 8. For the late, the total is 12. So the overall total 8 plus 12 is 20. And then for the red, early or late, the total is 13. For the yellow, early or late, the total is 7. Again, add 13 with 7, we have 20. Basically, this is what people call contingency table or cross tabulation table. What's nice about this kind of table is it provides the entire sample space. So you can calculate whatever you intend to calculate. We can actually calculate many different things if you have a table like this. Okay, we can probably add a little line to separate them. Okay, so you can see on the margin we have totals. If you forget about the total, we are looking at individual cases. All right, so I like to think of them as the joint event and the simple probability. For example, if you want to calculate a simple event, such as what if I want to calculate probability of red, right? What was the percentage of red in this 20 flower? You have to find the total of red. So what we're using in this case to find probability red is not anything in the middle, it's the total. So because we need to know the total flower that was red, so we end up having 13 as a total, but the total number of flower is 20. So we have 13 divided by 20. But if you want to calculate something else, for example, what if I want to calculate the percentage of early blossom flowers? And in this case, you need to find the total number of early flowers, and the total for the early will be the 8. So again, we're not using any number in the middle. We're using the total. We're using the marginal information. So we're taking the total, which is 8. That's the early for the total number of early flowers, and then the total will be 20. So 8 over 20 would be a simple calculation of probability. As usual, when you want to calculate probability of something, you need to have a number of outcome in that category, like for how many number was red, and then divided by the total. So that is the idea. But in this case, if you had a contingency table, individual number in the table will actually classify early and red, early and yellow. So these 5, 3, 8, 4, they're not representing individual like red or yellow or like, they actually represent a joint number, a number of a joint event. So for example, if we want to calculate probability of red and early, if you want to find the probability of an event, that's why you use individual number, because all these individual cases, they have a column information and they have a row information, and column information that's causing the information that the number of frequencies that we provide, it is actually a frequency for an event. I hope that can make sense. So if you get a table like this, what you are getting, red and which is 5, right? 5. So you're going to find this one. You're going to take the 5 and then divide it by 20. Okay. So this is how we calculate probability of AND events. Now, on the other hand, if you want to find the probability of OR events, such as probability of red or early, then you might involve, this has to involve multiple columns. The early is in this column, but the red is in the first row. So that means the first row and the first column. And the total is not going to be the 8, it's not going to be the 13, it's going to be early and red, which is 5 plus 8 and 5 plus 3 and then plus 8, which should be 16. If you think about the or, this is 16 divided by 20. Is 5 plus 3 plus 8. First column and first row. But anything that you counted, you only get to count it one time. So for example, early and red is first column, first row. If you think of this as a matrix, but then you can only count it one time. It occurs in the first column. It also occurs in the first row, but if you count it in the first row, you won't be able to count it in the first column. So it's 5 plus 8 and plus 3, that's 16. I hope that kind of makes sense. All right, you can also think of it, this is one event, this is one event, this is overlapping portion. For the overlapping portion, you cannot count it twice, 2 times, you have to subtract it. So if you do get the 8 plus 13, that will be 21, but then you have to subtract the 5. That's kind of the idea in the addition rule. If you add 2 of them, you have to subtract overlapping portion. Any question? All right, so this is using the contingent table kind of review. What was the probability calculation during a table? We went over how to calculate probability when you have a Venn diagram, but if you have a table, that's another way to classify or list the possible outcome in an event. Now, the question is to find a probability of red given it's early. This vertical line is what we call, we pronounce it as given. What is the probability of red given it's already early? So that it is suppose we look at all the early ones, we know the time, right? Some of the flower early, some are late. So you know this all these collection of flowers that's early. In that early group, you find how many red. Okay, and this can be easily find out. You already knew it's early, so it's in the early group. And how many of them are red? 5. So this calculation is what we call conditional probability. We're going to take the 5 and divide it by 8. We don't divide by 20 because we're not finding how percentage of red flower in the total. Percentage of red flower in the total will be 13 over 20. But we want to find percentage of red flower in the early flowers. So then the total is actually 8. So now this is called a conditional probability. The condition is whatever behind after the vertical line early is the total. You want to find inside the early flower, what was the percentage that was red? That's conditional probability. Any question? Conditional probability is useful whenever you know some information already given. In this case, we know it's red, and then you start looking inside it. We know it's already early. Inside the early flower, you find out what was the percentage of red. And so if there is there's a difference between what part is already given, what part is a condition, and what part is the one you were calculating. So. First example. So this is all we were talking about. Calculations for probability R given early is 5 over 8. We have probability of R is 13 over 20. So then just try to summarize what's going on. So you can see this is a verbal description of what happened. And obviously the table itself conveys more information in a more concise way. If you explain things in English or in words, it tends to be much more lengthy. And we very likely, as a mathematician, you might be, hey, that's hard to understand. Let me draw a picture. So we tend to eventually go back to the picture representation of things. All right, or table representation of things. We want to have information as organized as possible and as concise as possible. All right, let's define conditional probability. The conditional probability of an event, given the event A, given the event B has occurred, is defined by P of A given B. So B is now the condition. Now, if this is how you write your conditional probability, the calculation of it will be probability A and B divided by probability B. So B, or the probability for B, has to be in the denominator because B is a total. Please consider inside all B, what was the percentage of A? That's the idea. Inside B, what was the percentage A? This is assuming A and B has interaction. If B and A are mutually exclusive, then this conditional probability will be 0. So this conditional probability can only be useful if they are A and B, they overlap. And then in that overlapping part, you want to see the size of the overlapping parts. Now, if A basically is in B, then this will be 100%. That is, if B happen, A absolutely gonna happen if this is equal to 1. And that's like A is really small, right inside of B. Of course, that will be 100%. But if A and B is, if A is inside B, this is 100%. But if A and B only overlap a small portion, then this numerator will be small and this will be a small probability. Right, this is assuming probability B is larger than 0. If this is equal to 0, then of course the whole thing equal to 0 also. So then we don't calculate it with division anymore. If the probability B equal to 0, then things are differently defined. Okay, let's look at a couple examples. The first question says suppose probability A is 0.4, probability B is 0.5, probability A and B is 0.3. Then here we are, the probability A given B, that is, B is the total. B is the total. So conditional probability essentially thinking that inside a small total, what happened to the event A, right? So it's saying if you only look at inside B, what was the percentage of A? Now, A and B overlapping by 0.3. Now B is 0.5, so 3/5 will be the probability. Now, if you only look at inside A, what is probability of B? Or percentage of B inside A. So A has 0.4, so the denominator is 4, and the numerator will be 0.3. So 0.3 over 0.4, that's 0.75. Any question? The main purpose of this example is showing that probability A given B and probability B given A, they are not the same. Not the same. So it's really important to know what's are we calculating probability A given B, or are we calculating B given A, because they're totally we don't want to mess it up. It's another example. All right. The question that we had earlier. All right, this is a different question. All right, suppose the information is not given by a table and it's not given by equation. Suppose the question is given by this. Let's see, we still want to calculate probability A given B. So what will be the answer? Like, what is the percentage of A inside the B? That is what conditional probability means. What is the answer?
Should be 2/3.
2/3, yes. So the calculation will be, right, so if you want to calculate probability A given B, the numerator should be probability of, numerator should be probability A and B and B, because you want to look at how much is A inside the B. So the denominator has to be B. Probability B. And this is based on the definition that we had in the part. This definition. So the B will be the denominator, numerator will be probably A and B, and then all you have to do is look at the actual number for each one of these. The probability of A and B in this picture is 0.2, and the probability of B will be the total over B, and the total over B is 0.1 plus 0.2, which is 0.3. So the denominator will be 0.3. And the answer to the question will be 2/3. Any question? This is really a couple example understanding conditional probability. All right. Another question. Sometimes we can have a really complex question, and in order to calculate it, we have to follow the definition. It says, suppose you're rolling two four-sided dice. Number one, four-sided dice is a little rare. It's kind of little, four-sided, 1, 2, 3. Is three-faced pyramid, right? Pyramid with three faces and then one bottom. So you have three triangles at the side, one triangle at the base, so four-sided die. And normally we'll write 1, 2, 3, 4 on all four different sides. You roll two of such dice. Right, one dice will have an outcome of 1, 2, 3, 4. The second dice would show 1, 2, 3, 4. So altogether, if you think about together how many outcomes possible when you are rolling two four-sided dice, then the outcome will be 4 by 4. There are 16 possible outcomes. They're all in the table here. Well, you can call this like a list of the possible outcome using the pointer system. Now, having that, it's like having the sample space. Having all outcome listed in front of your face, it really helps when you try to figure out probability. That's kind of nice to have it ready. Many times we don't have the sample space, but when it's possible, we want to have the sample space drawn out. So in this case, we want to find probably I roll a sum of 3. Suppose the sum is 3 or 5. So number 1, you want to find out the denominator. So this is a conditional probability. So the calculation is, we got to find out what is the probability of the denominator. So according to the definition, it's equal to, the denominator will be the condition. The denominator will be the probability of sum equal to 3 or 5. That will be the denominator. Now the numerator will be rolling a sum that equals 3. So the numerator will be probability of sum equal to 3. It cannot be 5 because we want the sum to be 3. So this is, denominator is probably B and numerator is probably A and B. And it is smaller than B then. So that's what we intend to calculate. So then we can start realizing how many is in 3 or 5. This is all the total being 3. The only outcome of 3, total of 3, that's 2 of them. For the summation to be 5, there are 4 of them. So 4 plus 2 is 6. So the denominator will be 6 over 16. That's the probability, and numerator will be the sum being a 3. That will be 2 over 16. So altogether, we cancel the denominator 16, which is 2 over 6, and then you can simplify even further. That will be 1 over 3. So answer to the question is actually 1/3, assuming the condition. This is like knowing the summation is 3 or 5 to find out how likely it is 3. So obviously 5 is more likely than 3 if you already knew the summation is 3 or 5. Any question? Right. Conditional probability, to me, it felt like you have previous information and now you want to find out how likely for the new information. This is previous information is already there. All right, this is that example. Okay. This is a situation when the given information is a verbal description of what's going on, and we want to calculate. I guess the answer is already in the question description. A county fair carnival game. There are 25 balloons on the board. 10 balloons are yellow, 8 are red, 7 are green. A player still starts at the balloons to win a prize and randomly hits one of them. Okay. Given that the first balloon hits is yellow, what is the probability that the next balloon hits? It is also yellow. Okay, of the 24 balloon, all right, so it's 10 plus 8 plus 7. The total is 25, all right? 25, right? So this is the conditional probability that I want to consider. Let's look at the situation. So we're actually talking about 2 hits, and the first one is yellow. And what is the probability? The second one, it says first hit is blue. How likely? What is the probability? Next balloon hit is also yellow. So we're thinking about, assuming you already knew the first one is yellow, what is the probability that the second one is also yellow? Sometimes we do try to analyze it with the tree diagram. This question, the answer is already there. The answer is this 9/24. So we can kind of draw the tree diagram for the first hit. Okay. We have yellow, red, and green. The is 10, 8, and 7. So the total is 25. So for the yellow, you get 10. The total is 25. So probability for yellow is 10/25. Probability for red is 8/25. I'm drawing probability on the line for the tree diagram. Probability for green will be 7/25. All right, but then we're talking about second, no, you already hit one, and that was the yellow. So now with that assumption in place, that is previous information. Our previous information is you hit a balloon that is yellow. Now, under that assumption, what is the probability the next one would also be yellow? So our next hit could also be yellow or red or green. The tree diagram can go on a bit. So this line is our question. That is, assuming the first one is yellow, how many balloons do we have? We only have 24 balloons. So the denominator will be 24 instead of 25. And numerature, since we hit a yellow balloon, right? We only have 10. The 10 yellow balloon was at the beginning. We only have 9, so it should be 9/24. The yellow, right? So this is, if you have to write it, it's probability of hitting a yellow balloon, which is the second hit, assuming the first one is also a yellow balloon. And that's what we know, the first one is already yellow. That's why we only have 24 balloons to hit. And there's only 9 yellow balloons to hit that. Denominator is the total number of balloon, numerator is total number of yellow balloon after the first hit. Are we okay? So the representation for the 9/24 is actually a conditional probability. And when we are trying to attach probability onto the tree diagram, the first layer of the tree, that is a pure probability of yellow, probability of red, and probability of green. But then the second layer on the line, we normally write on conditional probability because you can only calculate probability under that situation, right? So then the probability are going to be different at different point. For example, if we finish the tree diagram here, I mean the 9/24 is really important for this one, but then we can have more questions. What is the probability of hitting a red, assuming the first one is yellow? So what is probability of red, given that it's already a yellow in the first one? Again, the total will be 24 since we hit the first balloon. We only have 24 balloons to hit. The 24 is the total number of balloons. So how many red in that 24? 8. So that's that one. What about the green? 7/24. So at every layer of the tree diagram, the total should add up to be 1. So 9 plus 8 plus 7. The total is 24. All the numbers are add up together. In that case, we can do the same for this layer, running out of space. So yellow, red, and green. So the tree diagram can be finished for however number you're trying to do. But as we go on and on for the second layer and the second layer of the tree, drawing it might be difficult. Right around physical space. So for example, if the first one is red, then your denominator is still going to be 24. But then if the first one is a red, then you still have how many yellow balloons? You still have 10 yellow balloons. So it's 10/24 in that case. So all these numbers that we're trying to fill out, they are conditional probability. Again, just try to explain the difference between conditional probability under different conditions. See, this is 10/25, and then become 9/24. Or if this is red, then this will be 10/24 instead of 9/24 or 10/25. These are all calculations for yellow, but this is under different condition. Well, the condition is different. The probability for yellow will take on different value. Any question? Right. Just try to explain having different condition causes the probability of yellow change from case to case. Example. Okay, now that we have conditional probability, we're ready to talk about multiplication. If you had other probability or read the probability book before, addition rule and multiplication rule are two of the most famous rules for probability. In a sense, the addition rule allows us to formulate logic for calculating probability A or B. Now, multiplication rule allows you to calculate probability A and B. That is assuming direct calculation is not possible. Again, the direct calculation will be probability of any event is number of outcome in the event divided by the total number of outcome. But if that's not available, that is often caused by not having the whole sample space. So if you only have partial information, that's when the rule can be helpful. All right, it says the probability A and B can be calculated using two different ways. Number one, if A happened first. So if you want A and B means A happened and B happened. So that since these are two different events, which one happened first can be random. So suppose A happened first, then you want B to happen under the condition that A already happened. So probability A times probability B given A is one way to calculate probability A and B. Or you can calculate probability A and B by, let's say, B happened first. If B happened first, and since you want A and B both happen, now you want A happen on the condition that B happened first. B already happened. So this is another way to calculate probability A and B. It doesn't have to be that A happened first or B happened first. You can calculate either way if it's logically possible to find that information. So this is two different formulas for calculate A and B, and both of them are called multiplication rule because the fundamental reasoning is it's kind of like the multiplication rule is step 1, A, step B, step 2, B happen. But that's assume since this is A happened first, so then the second one end up being conditional probability. So the reason that second one is conditional probability is that we're assuming that this one is already there. Any question? All right, so you can see if we don't have conditional probability, it's harder to talk about multiplication rule. And let's look at an example. A bowl contains 7 blue chips and 3 red chips. 2 chips are to be drawn successively at random without replacement. So you take it out and don't place it back. That's called without replacement. We wanted to calculate the probability that the first draw result in a red and the second draw result in the blue chips. Okay, so the logic is 7 blue, 3 red. The total is 10. So the calculation for red is 3 out of 10. There's 3 red, 3 over 10. And then we already knew the first one we wanted to be red, and second one we wanted to be a blue. But there's only a limited number of chips, and we don't put it back. So after you take 1 red chips out of it, you only have 9 chips in the bowl. Out of the 9 chips, one of the red was taken out. So how many? Oh, we want a second one to be a blue. So how many blue would have 7? So there are 7 blue chips in the 9 in a total of 9. So 7 out of 9 is assuming the first one is red. What's the probability for the second one to be blue? So then we want to ask the question: how likely for it to be first red and second blue? So this is red and blue. For the first one to be red, this is probability. For the second one to be blue, this is probability. We multiply together, the total is 7 over 30. Since we are talking about 2 different draws to draw, first draw and second draw. Any question? All right. As you can see, the probability for blue is not 7 over 10. It's 7 over 9. The change from 10 to 9 causes change of the total. Therefore, this is not probability A times probability B. It's probability of A times probability B given A. So the first one having a red affected the second blue, right? Without the second one being second one, we wouldn't have 7 over 9. We would have 7 over 10 if you're only talking about blue probability. Probability for blue in the original bowl it will be 7/10. Now it's 7/9 because we have first draw. Okay, so this is a situation when using the conditional probably is necessary. Any question? All right, so this is using the multiplication rule. Below we have another logic of it. We're going to find out, what if we want to find out probably a red and red, meaning the first one is red, the second one is also red. Probability is 3/10 is the first red, 2/9 is the second red, so the total is 1/15. Another question. Another way to do the calculation is think about, this is like choosing 2 chips out of 10 chips. So 10 choose 2. That's the total, that's the denominator. The numerator, since we only want 2 of them to be red, so out of the 3 red chips, we choose 2. And that is, we only want to choose 2 red chips. Now, other colors, that also end up being 1/15, which is the same as what we would have in the multiplication question. So the second section, we're talking about enumeration. We're using combination number or permutation number. As you can see here, sometimes the combination number and permutation number might provide an alternative way for the calculation. So you can use multiplication rule, or you can use the combination number as a way to count number outcome for the numerator and denominator. This is 2 different calculations of the same thing. Any question? Couple other similar example. This one says a barn contains 8 1-hump camel and 7 2-hump camel. The camel come out of the barn randomly, one at a time. Probably that 7 camel that comes out of the barn is third 2-hump camel. To do so can be computed as follows. So let A be the event that 2-hump camel it's a tongue twisting come out among the first 6 camel, and let B be the event that the 7th camel come out has 2 humps. Then the probability that we wish to calculate it would be A and B. All right. The event itself is already pretty complicated. The 7th camel that comes out of the barn is the third 2-hump camel. Okay, so basically we have a target. Number 1, we want the 7th camel to be a 2-hump camel in the first place. And then on top of that, we want the first 6 camel to have 2 2-hump camel, right? For the 7th one to be third 2-hump camel, you already have to have 2 2-hump camel before the third 2-hump camel before the 7th one, right? Right, so among the first 6 camel, you have to have 2 2-hump camel. And then all we have to have is the 7th one to be a 2-hump camel. And that's why we kind of separate them. Because the first 2-hump camel, you don't care which one is 2-hump, which one is 1-hump. As long as the total number of 2-hump camel is 2, and that means the 1-hump camel would be 4 among the first 6 camel, right? The order can be random in the first 6 camel, but then the 7th camel gotta be a 2-hump camel. Then that will make the 7th camel be the third 2-hump camel in that case. So we separate the 2. That's why we have the assignment. The A has to be the event that the 2 2-hump camel come out among the first 6 camel, and B will be the 7th one, gotta be a 2-hump camel. All right. Now we can start calculating it. The B is actually easier to have. You already have how many camel? You already have 6 camel is out. The total number of camel is 8 plus 7. 8 plus 7 is 15. So total number of camel is 15. But assuming we're talking about B here, talking about 7 camel, that is assuming you already has 6 camel out of it, right? So 15 minus 6 is 9. The total number of camel that are still in the barn is 9 camel, right? Right? We already talked about A, assuming A already happened. A says that the two hump camel is in the first 6 camel. So how many 2 hump camel is in there? We have 7 2 hump camel, and we're assuming 2 of them are already out. So to make sure this is the third one. So then 7 minus 2 is 5. Numerator gonna be 5. In that 5 camel left in the barn, one of them gotta be the 7th one. Okay. So B is the one, the B given, probably B given A is the one that's slightly easier to calculate. You can just find out number in the outcome B, assuming that A already happened. All right, A is the one we have to carefully consider, and the calculation presented in the book is using combination number. That is in the first 6 camel that comes out of barn. There are that six camel, first 6 camel come out of the 15 camel. Total number of camel is 15. So 15 choose 6 should be in the denominator. All right, in the numerator is assuming in that 6 camel that comes out first. In that 6 camel, 2 of them is 2 hump, and then the other 4 must be the 1 hump, right? So yes, it needs a little editing here. So then that will be 6 camel. Then in that 6 camel, 7 2 hump camel in total, then we're going to choose 2 because in that 6 camel, we needed to be 2 hump. Let me try to color this to make it more visible. And it does not allow editing. So let's try to highlight the A here. 2 out of 6 are 2 humps. The first 6. All right, so this is the total number is A plus 7 is 15. So the denominator is 15, choose 6, and numerator is out of the 7 2 hump camel, you choose 2. Out of the 8 1 hump camel, you should choose 4. It should be 4, right? That 2 plus 4 is the 6 camel. In that 6 camel, 2 of them is 2 hump. 4 of them is 1 hump. That will guarantee inside the first 6, 2 of them is 2 hump. I think the final number was right, and that one was wrong. That one should be 4 because we are talking about total number of camel being 6 and the 2 hump camel being 2, 1 hump camel being 4. Question. This can be double checked. Put into a calculator, and instead of C, we should choose 15. Choose 6 is the denominator, and numerator should be 8. Choose 4, and 7 choose 2. 7 is the 2 hump camel. Try to confirm the number here. So if you calculate those combination number, you get 0.2937. So the number itself is the same as in the text. I think I have that coefficient wrong. Any question? So once we find out probability A and probability B given A, all we have to do is multiply the 2, and that is the probability to have the 7th camel being the 3rd 2 hump camel. That is the event. Any question? All right, we might come back to this. I think this probability that we're talking about is called hypergeometric. Something similar to that. All right, let's try to move, make a general idea. What about the multiplication rule for 3 events? That is probably A and B and C. So you want all 3 to happen at the same time. You want all 3 to happen So you can again use the multiplication rule repeatedly. You can combine A and B as one. So you would say probably A and B and probably C given A and B. So that we separate them. And then this probably A and B according to the multiplication rule with this. And then altogether we have the last one. The last one is a formula for addition rule, multiplication rule for three events. So probably A and B and C is equal to probably B times probably B given A times probably C given A and B. You can think of a sequence of events. So if you want A, B, C all happen, let's say A happened first, then you want B happen under the condition that A already happened, and then you want C happen under the condition that A and B already happened. So conditioning on A and B. So that logically it is okay. So that make it possible for us to kind of connect the formula and understand the formula. Any questions? So this is where in the situation, if you need to calculate the joint probability of all three. Questions. Basically, the first one is derivation. The last one is the actual formula. Let's look at example. 4 cards are to be dealt successively and random. A deck of cards have 52 cards. Okay, the probability of receiving in order a spade, a heart, and a diamond, and a club is the following. You can look at a deck of cards. Whenever I'm confused, I'll just go ahead and look at a picture. The deck of cards looks like this. This is called a heart, right? What's the name? Which one is called a club? That's club, right? Club. And this is diamond. Diamond, hearts, spade, and club. So basically, there are 13 of each. The total is 13 times 4, 52. So if we want to calculate, see here, we want to calculate the probability of a spade, a heart, a diamond, and a club. So how many spades do we have? We have 13. So to have the first one being a spade is 13 over 52. And then now that you have one card taken out of it without replacement, that's why that way we don't have 52 card anymore since we take one card out. So total becomes 51, right? But we want the second one to be a heart. So how many hearts do we have in that 51 card? We have 13. And now we have 50 card left. How many diamonds do we have? Which again is 13 plus 13 over 50. The last one, how many clubs? The total number is 13. And that's the first club we're drawing, but the total number of cards is already reduced to 49. And that will be the probability. So this is a joint probability calculation successfully. You're going to calculate each one of them, assuming you understand the new total. See, the total has been increasing. Question. Okay, if we were putting it back, it will be 13 over 52, 13 over 52, 13 over 52. The reason the denominator changes because we keep the card without putting it back. All right. See, something new. All right, this one is one I think we should talk about. So things are related. Things that one affect the other often is the kind of situation we want to look at conditional probability. This is one example that we should talk about, which relates to insurance and insurance policy, which is what actuarial science student might have to consider. And in the text, we actually have an example from physics about circuits. See, in the homework, we got Also have a question that relate to. Right, 1.3, we have. Similar to what we're doing, the table question, the a container question, the container has multiple scenario. Which one? To circuits. To pull that question out because we have similar problem. Okay, this one is where you set up a circuit. Right, this is something you might encounter again in your physics class. And then, for example, 1 and 2, it has to be both connected. So 1 and 2 has to be together. If one of them is open, then the current cannot go through, right? Then it's not functioning. But between this line and this line, there is a OR relation. So you can have this one or this one. As long as one of them is closed and the current can go through from A to B. There's a logic relation here. Between the 1 and 2 is a and relation. Also between this part 1, 2, 3, 4 and then 5 is a and relation. But between 1, 2, and 3, 4, 1, 2, and 3, 4, they are a OR relation. You either have 1, 2 close or you have 3, 4 close. You don't have to have both. So that is something we are able to solve with our additional and multiplication. Now first let's look at this example. All right, so insurance sells several types of insurance policy, including auto policy and homeowner policy. A1 be those people with an auto policy, only A2 those people with a homeowner policy, only A3 those people with both and both auto and homeowner policy, but no other policy. If a person randomly selects from the company policy holder, suppose PA1 equal to 0.3, PA2 equal to 0.2, PA3 equal to 0.2. Right. Let B be the event that the person will renew at least one of these policies. So from the past experience, we assign the conditional probability, right? So B would be the probability of renewing. If the person has a A1, then renewing has a 0.6 probability. If it's A2, then the renewing probability is 0.7. If it's A3, the renewing probability is higher because this will be a person that holds both policy, auto and homeowner. So the more heavily you invested in the insurance company, the more likely you renew. And it's obviously a higher probability for renewing. Right, given that the person selected at random has auto or homeowner policy, what is the conditional probability that the person will renew at least one of these policies? So basically, if we are trying to calculate the probability of renewing it, so we're trying to calculate the probability of B, basically. Okay? So you have to calculate all three. You have to calculate B and A1, B and A2, and B and A3. So the probability of B is being classified or partitioned into three different scenarios, and then you were supposed to add it all together. So if we were to look at it, we count this. All right, so we want to calculate, essentially we want to calculate probability of B renewing the policy probability B. And then you can see A1, A2, A3, they're not overlapping. A1 is the one only have auto, A2 is the one only have homeowner policy, A3 is the one that has both. So with the word only, auto only, homeowner only, and then with both. So there are three different ones. If you have to draw the Venn diagram, it's kind of like this. I guess I should clean the space before I start drawing it. Okay, so it's like having the three area labeled one by one. Okay, so A1 is the one that has auto, so this is A1. And then A2 is the one that has only homeowner, so this is A2. And then A3 is the one that has both, so this is A3. I'm trying to explain that they're not same. It's a different scenario. So to calculate B, you would do probability of, probably almost all the time, B and A1, and then plus probability of B and A2. And then lastly, you should also you should calculate all three, plus probability of B and A3. That should be all three different scenarios considered, right? And then to calculate each one of them, you do the multiplication rule. So for probability B and A1, if you take the A1, multiply by B and A1. So that will be A and A1. So to calculate N probability, you will use the multiplication rule. You take the A1 times B and A1. For the second one, you take A2, multiply probability B given A2. And the last one, you take the probability A3 and multiply by probability B given A3. You have three pair multiplication and you add it all together. Any question? All right, we'll give this a special name. It's called a calculation of total probability. And this is the answer to the question. Oh, condition. What I was calculating is a numerature. I multiply, and add it together. Is there a condition here? Yeah, it did say, it says given that this person is renewing, given that person, given this person does have a policy, so we would have the total number of policies added together. So I thought the denominator would be 1, but it's not. So you have to take the A1, A2, A3, add it together as a denominator. I was just calculating the numerator when I was trying to go through the calculation. It looks like it's time for the class, so we'll stop here for today. I think you should be able to start your 1.3 homework. If we have any questions, we'll come back to it on Wednesday. Any questions? That will be it for today. I'll see you on Wednesday. Thank you. That's the answer to the question.
They're in one folder right now.
Yeah, I've been trying to really work on everyone else, because that's hard. I went through all the problems.
I'm finally starting to understand like the principle of like how to prove.
Yeah.
And the moment.
But the issue is like,
He didn't tell us what the structure of a proof would look like for that. He just like, here's what these things are, by the way, now let's do some proofs. Like, I didn't know exactly what we were doing all with that.